Hello, and welcome to this training session for SmartEP-ASSR Auditory Steady State Responses by Intelligent Hearing Systems. Today, I will walk you through the software operation and analysis for ASSR testing. ASSR offers an objective test measure that provides frequency-specific threshold information. ASSRs are evoked potentials elicited by the presentation of either continuous tonal signals or fast-rate short-duration sounds. While an AEP, like the ABR stimulus train shown on the top graph, presents a single stimulus per sweep, an ASSR stimulus train, as seen on the bottom graph, presents multiple stimuli per sweep. Using faster rates causes the auditory evoked response to one stimulus to overlap with the response of the following stimulus, as shown here. As we can see, ASSRs are composed by the repetition of early and middle latency auditory evoked potentials elicited by a quick and repetitive stimulus train. As depicted here, the stimulus is delivered to the ear at a certain modulation frequency or rate of stimulation. ASSRs are usually elicited by using a stimulus with characteristics of specific carrier frequencies, most commonly 500 Hz, 1000 Hz, 2000 Hz, and 4000 Hz tones. The SmartEP-ASSR also includes options for click, 250 Hz, 8000 Hz, eye chirps, and other complex stimuli. The region of the cochlea being stimulated corresponds to that of the carrier frequencies. Responses are then generated along the auditory nerve in the brain that mimic the modulation frequency. Modulation frequencies from 20 to 120 Hz can be used. In practice, the best results have been obtained using modulation frequencies above 70 Hz. These faster rates of stimulation produce responses that have larger contribution from the earlier ABR components, therefore making these modulation frequencies less susceptible to being affected by patient state. And the use of these allow patients to sleep without affecting the responses. As you can see on the slide, changing the modulation rate will affect the ASSR response structure. Slow modulation rates between 20 Hz and 40 Hz elicit the middle latency response or MLR components. These modulation rates can result in large amplitude responses. The caveat with using these slower modulation rates is that they are affected by patient state. In other words, if a patient falls asleep while testing using these rates, the response will disappear. It is important to also keep in mind that MLR components are also affected by the maturation of the auditory system. Fast modulation rates between 70 Hz and 110 Hz elicit the ABR components and result in lower amplitude recordings. But like the ABR, these responses are not dependent on patient state, making these the preferred range of modulation rates used in the SmartEP-ASSR software. There are two ways to modulate a stimulus. You can modulate the amplitude as well as the frequency. Here are some examples of amplitude modulation applied at different modulation depths. Applying 100% amplitude modulation is equivalent to turning off and on the sound signal. Here is an example of frequency modulation. This means the frequency changes through time as the sound signal is presented. This is also known as jittering the frequency. When frequency modulation is used, the cochlear stimulation region is typically broadened. Combining both amplitude and frequency modulation has a dual effect on the cochlear generation site. When using this method, the time relationship between the maximum amplitude and the maximum frequency is critical in eliciting optimal responses. These two should coincide in order to elicit the largest possible response. Let's review frequency specificity and neural synchrony. Here is a graphical table that can help us understand how the stimulus characteristic of an electrical signal translates to its frequency content and how it affects the recorded response. For example, clicks are short-duration stimuli. As such, they have a broad frequency content and stimulate a wide range of the cochlea outer hair cells, thus producing a greater amount of neural synchrony and resulting in robust responses. When it comes to frequency-specific tones, the duration and shape or enveloping of the stimulus will dictate the frequency specificity of the response. As shown in this example, a tone with a 5 millisecond rise time has precise frequency content because a more narrow region of the cochlea with fewer outer hair cells is being activated, which leads to less neural synchrony, resulting in recorded responses of smaller amplitudes. The repetition of transient stimulus, as used to generate ABRs, can also be used to generate ASSRs. It is believed that the short onset durations of transient signals produce greater synchrony of neural discharges. Therefore, they in turn should produce stronger, more robust responses as compared to the longer onset or rise-fall times of amplitude-modulated stimuli. This is the reason why IHS turned to transient types as the default stimulus for the SmartEP-ASSR software. Transient types of stimuli include clicks, short-duration pure tones, frequency-centered tone chirps, or I chirps, and band-limited noise signals. The SmartEP-ASSR system uses Blackman tones to preserve frequency specificity without compromising neural synchrony. Here in black is a depiction of one of the complex multi-frequency stimuli used in the SmartEP-ASSR using 4 Blackman tone components. A representation of its 4 carrier frequency components and stimulus characteristics can be seen overlapped above it. Now let's review some important concepts and definitions regarding ASSR analysis. These concepts need to be understood before you begin testing, as they will have an impact on how you manage your test protocol. The amplitude spectral analysis provides spectral amplitude information across all frequencies. When you acquire an ASSR response, you will see time domain data on your screen or an ASSR waveform recording. That time domain data has a phase value, an amplitude value, and a frequency value as shown on the top graph. These values are not easy to visualize in the time domain. When you analyze the recording in the frequency domain, meaning you run a fast Fourier transfer or FFT analysis of the response, you easily obtain discrete frequency and amplitude information as shown on the spectral frequency domain graph. By looking at the frequency corresponding to the modulation rate of the stimulus, valuable information about the response to the carrier frequency can be obtained. The analysis screen will also provide phasor information via the phasor polar plot. A vector or phasor on a phasor diagram represents the amplitude and phase of the recorded response, where the phase represents a measure of time displacement. In other words, the time from the onset of the stimulus to the occurrence of the response is the phase of the response. Unlike an amplitude spectral display, which shows amplitude information across all frequency, the phasor vector only represents the discrete frequency of the plotted phasor. If multiple phasors are plotted, each one represents the measured response at different, specific carrier frequencies. Repeatable and robust responses will show a tight distribution circle at the tip of the phasor, as shown in the top figure A strong response. As the stimulus intensity of the carrier wave decreases, the amplitude of the response will also decrease, and the phase distribution will widen as shown in figure B, weak response. Below threshold levels, the phasors will have a random distribution near the center of the phasor graph, as shown in figure C, no response. Due to the nature of the ASSR methodology, information for both ears can be gathered in a single recording by stimulating both ears simultaneously. By using various repetition rates or modulation frequencies, various carrier frequencies can be combined and tested simultaneously. For this to work, each stimulation carrier frequency in each ear must have a unique modulation frequency. This way, we can differentiate between the responses. Left ear responses are displayed here in blue, while right ear responses are displayed in red. Each carrier frequency will generate a response at the modulation frequency. The frequency analysis seen here shows 4 carrier frequency responses for the right ear, each one in red. Response determination is conducted the same way as when using a single frequency, by measuring the amplitude and noise for each frequency at the corresponding modulation frequency. In this example, complex stimuli made up of 4 main carrier frequencies, 500 Hz, 1000 Hz, 2000 Hz, and 4000 Hz, are being delivered to each ear, with each carrier presented at different repetition or modulation frequencies. For the left ear, the 500 Hz carrier frequency component is being delivered 77 times per second. 1000 Hz is being delivered 85 times per second. 2000 Hz is being delivered 93 times per second. And 4000 Hz is being delivered 101 times per second. While for the right ear, the 500 Hz component is being delivered 79 times per second. 1000 Hz is being delivered 87 times per second. 2000 Hz is being delivered 95 times per second, and 4000 Hz is being delivered 103 times per second. Each carrier frequency will be stimulating its respective region in the cochlea, and the auditory system responds at the same modulation frequency or stimulus rate, matching the stimulus input. Therefore, when you convert the time domain ASSR response to the frequency domain, you obtain discrete responses for each carrier frequency, 500 Hz, 1000 Hz, 2000 Hz, and 4000 Hz. For this example, response information can be found at the frequency response bins of 77 Hz, 85 Hz, 93 Hz, and 101 Hz respectively for the left ear, and 79 Hz, 87 Hz, 95 Hz, and 103 Hz respectively for the right ear. Here is the ASSR analysis display screen in the SmartEP-ASSR software. A spectral analysis of the signal and noise estimate is done to look at the frequency components corresponding to the modulation frequency of the stimulus and the surrounding spectral bins. We see 4 carrier frequencies were tested for each ear with different modulation frequencies, thus eliciting responses in distinct frequency bins on the frequency domain plot. Responses are detected in the frequency domain by comparing the signal and noise characteristics at the modulation frequency to the corresponding values at the surrounding frequencies. Values used for response detection are available on the screen by activating the Show Table option. Now let's begin to discuss response detection. In SmartEP-ASSR, objective response determination is made possible by placing acquired data in 2 different buffers. This technique is called a split sweep technique. The 2 buffers are then used to determine the signal and the noise level in each recording. Even sweeps are averaged internally in buffer A, while odd sweeps are averaged in buffer B. The response signal is then made up of buffer A plus buffer B, while the noise signal is made up of buffer A minus buffer B. Response detection involves using this buffer information to calculate the signal-to-noise ratios. Typically, the amplitude of any individual component will vary greatly, generally between 0.08 and 0.01 microvolt, depending on the stimulation intensity, carrier frequency, and type of signal modulation. Due to this variability, the absolute value of the response is only part of the factors used when determining the presence or absence of a response. Other values, such as its amplitude as compared to the noise, are also considered in order to avoid false response detections. For this purpose, SmartEP-ASSR uses the following response criteria. The minimum response amplitude must be greater than 0.0125 microvolts. This is the first horizontal line on the spectral analysis graph. Your red and blue responses should be above this line for it to be considered a pass response. The second criteria is that the signal amplitude minus the noise amplitude, also known as the signal-to-noise ratio or SNR, in the response bin must be greater than 6.13 dB. The third criteria is that the SNR of the side bins, which are the 5 bins or 5 Hz on either side of the response bin, must be greater than 6.13 dB. Lastly, the final criteria is that the noise level of the recording measured at and around the modulation frequency must be less than 0.05 microvolts. This prevents excessively noisy recordings from being evaluated. As a clinician, you will want to monitor the data table for these 4 response criteria. It is in your best interest and a great testing strategy to use this information to determine your own stopping criteria. For example, if there's an NA or very low signal-to-noise ratio listed in the signal, column number 1, or sidebin, column number 4, for any carrier frequency being tested, and it's the only pending carrier frequency waiting to obtain a response, then as a clinician you can determine that there is no chance to pass that frequency and decide you may want to stop the acquisition. This will enhance your test times and your outcomes. This table shows the relation between SNR and the significance level. The SmartEP-ASSR software uses an F-test or F-statistic calculation based on 10 degrees of freedom, corresponding to 5 frequency bands, each one with a bandwidth of 4.88 Hz on each side of the response frequency band. Using an F-statistic, a response is considered to be present if the signal-to-noise ratio, or SNR, is 6.13 dB above the noise at the response frequency bin and 5 Hz on either side. As shown on this table, the SNR value corresponds to a p-value of less than 0.050, or a 95% certainty or significance that a response is present. Statistically, if a large number of degrees of freedom is attributed to any measure, very small differences may become significant, thus reducing the accuracy of the response detection algorithm. In addition, since the spectral distribution of averaged EEG is not random, it is important not to overestimate the number of degrees of freedom. The SNR estimate implemented in SmartEP-ASSR using a smaller number of degrees of freedom and broader noise frequency range provides for a conservative response detection criteria. Additional response criteria can be activated by the user in the SmartEP-ASSR analysis screen. These options are the 4-point harmonic components and the phase criteria. Activating the harmonic analysis box will enable the display and evaluation of the harmonic components. It will expand the display of the FFT graph to include higher frequency components past the standard 152 Hz. This option increases the chances of obtaining responses by adding bins of interest where a response can be present and replicating. Activating this option can certainly speed up response detection. It is a good testing strategy to always have the 4-point harmonic analysis activated in the analysis screen, and save this selection as part of your default settings files. When using iChirp stimuli, the amplitudes of the harmonics may be significantly higher. Enhanced signal amplitudes combined with harmonic information make the automated detection of steady-state responses easier and more robust, thus increasing the efficiency of ASSR testing. Activating the phase criteria will evaluate the standard deviation of the phase, helping identify if a response is variable or stable. If the phase standard deviation at a response frequency bin is greater than 80 degrees, it will not be considered as a response. Keep in mind that activating this option will make your response criteria stricter and may delay the detection of responses. Before you begin testing, and if you wish to have the software automatically stop acquisition, you may want to set up some acquisition stopping criteria. There are 3 main stopping options that you can activate or define in the software. The first 2 are found in the protocol menu. The first is Auto Stop All Response. When activated, the system will only stop acquiring if it has detected a response for all of the carrier frequencies being tested. The next one is the Auto Stop Level. This is a criteria based on residual noise, and it is measured in the time domain as the peak-to-peak amplitude of A minus B. The level is user selectable. IHS recommends a residual noise level of 0.7 microvolts, as our studies have shown that averaging past this level does not increase your signal-to-noise ratio values. The residual noise value can be seen on the information bar as circled at the top of the screen, or on the noise plot, which is only available during acquisition. The highlighted green line, as shown in this example, shows an auto-stop residual noise level criteria line of 0.7 microvolts is selected. The third stopping option is based on the maximum sweep count. This rule takes precedence. In other words, regardless of the auto-stop rules that are activated, the system will definitely stop the recording average when it reaches the maximum sweep count, as specified here. Moving on, there are various ways to set up your amplifier input channel, but the default for two-channel system is always dual channel A and B, where both channel designations are set to on. This means that regardless of the ear of stimulation, you will always acquire an ASSR response from both channels, obtaining ipsilateral responses from the side of stimulation and contralateral responses from the opposite side of stimulation. This will increase the chances of obtaining a significant response, since you will be acquiring ipsi and contra responses from both sides. Now let's review the patient supplies. Skin prep pads are used to prepare and clean the skin. If you need to reduce impedance, you would use the skin prep pad to re-clean the skin. Pat dry the skin after use. IHS recommends using Ambu Neurology disposable snap electrodes. If using a duet system, you would use a patient cable, either the 4-electrode snap lead patient cable or the 5-electrode lead patient cable with snap leads. Snap leads are available in red, blue, white on white, white on silver, or black. If you're using an OptiAmp system, you would simply connect the snap leads to the OptiAmp transmitter. For one-channel devices such as a USB Lite or USB Lite Solo, you would use the patient cables shown here. Here we see the electrode montage for doing ASSR testing. The most common montage is your typical two-channel ipsilateral and contralateral setup, as shown on the top two figures for the Duet and USB product platforms, where each test ear is connected to the negative electrode lead amplifier input, the forehead is connected to the positive amplifier input, and the lower forehead is connected to the ground. For one-channel systems, when using ipsilateral montage, automatic switching of the grounds is enabled. When testing binaurally, clinicians using one-channel systems may also choose a midline montage, as shown on the bottom right, where the nape is connected to the negative electrode, the non-inverting positive black or white electrode is connected to the high forehead, and the shoulder is connected to the blue or ground electrode. You should use the skin prep pad to clean the skin area at each electrode placement site, as noted in the electrode montage. Make sure to dry the electrode placement area thoroughly. When placing the snap electrodes on the patient, make sure to press around the white edge of the electrode to adhere the electrode to the skin. Do not press on the center of the electrode where the sensor sponge is located, since this area is full of conductive gel. If pressed, the conductive gel may spread and compromise the adhesive area around the electrode, which can lead to a detached electrode mid-test. If impedances are high, remove and discard the snap electrode. Remove any conductive gel on the skin and re-prep the skin with a skin prep pad. Pat thoroughly dry the electrode placement area and reapply a new electrode. Electrodes that are not conductive may require a dab of Spectral gel on the sponge area. Do not use electrodes that are expired, dried, or have been exposed to the elements. After you have prepped the skin and placed the electrodes, you are ready to begin testing. Typically, ASSR testing is done with standard insert earphones. If you will be using the bone conductor for testing, please note that bone conduction ASSRs can only be done one ear and one frequency at a time. Let's review the SmartEP-ASSR software main screen. On the top, you will find the main menu, an information bar, and the shortcut toolbar, where you will find the frequently used new or open patient icons, as well as the save or load report icons. The center white space is where you will see the ASSR time domain recordings displayed, as well as the SNR and residual noise graphs. Over to the right, you will see the default stimuli selection panel, as well as the EEG display, impedance check, and the Functional Analysis and Audiogram buttons where response determination takes place. Located at the bottom of the screen is the Acquisition Control panel, where you initiate tests by selecting the ears of stimulation and where you can increase or decrease intensity. To begin testing, first you need to enter a new patient into the database or load an existing patient file. Next, verify the EEG and adjust the artifact rejection window for both channels accordingly by using the open and close sliders. Check impedance by clicking on the Check Impedance button. If impedances are high or above 7 kiloohms, please reprep the skin and reapply your electrodes. For OptiAmp systems, impedance is checked at the transmitter box via the rotary switch. Next, click on the Stimulus menu and enter a starting value for the stimulus intensity and a maximum sweep count. If you will not be using the default stimuli or the Activate Stimulus Selection panel and wish to test using different stimuli such as eye chirps, then stimulus files can be loaded and selected for each ear by selecting right stimulus or left stimulus respectively from this menu. Otherwise, you can use the default stimulus available by checking your single frequency per ear or multi-frequency selection and clicking on the Activate Stimuli Selection button to load your stimulation configuration. Once active, the stimulus information listed at the top of the panel will update. Please note that at least one frequency must be selected per ear, although you do not need to stimulate both ears simultaneously. To start acquisition, click both for binaural stimulation, or right or left to initiate ear-specific stimulation and testing. Note the software will acquire data in blocks of 20 sweeps. Select Analysis to view the frequency spectrum of the response, along with the response detection data table and phasor plot. Or select Audiogram to view the audiogram results. Both of these can be opened while the sweeps are being acquired, and will update with every new block of 20 sweeps. Now let's explore setup and ASSR testing strategies. I have provided testing strategies throughout this video presentation, but here's an additional list of technical tips collected from clinical field observations. These are just suggestions, and you may have your own techniques that work better. The most important component of the setup is grounding, especially for the lowest amplitude ASSR responses. Please refer to the IHS Good Quality AEP video for more details. To get baseline information, a multi-ear, multi-frequency test at a high intensity, such as 80 dB SPL, is typically done as a starting point in the testing protocol. If the initial block of 20 sweeps is very noisy, stop the test and settle the patient down. Check environmental conditions and setup, and then restart. Otherwise, it will take a very long time to average out the noise. Setting up the ideal test conditions at the initiation of the test is critical. Drop in 10, 20, or 30 dB steps, depending on your clinic's typical protocol paradigm. As you decrease the intensity, remove the frequencies that are not responding from your stimulus presentation configuration panel. It's better to come back and test those frequencies later. As you approach the patient's hearing threshold, it will typically be more difficult for the patient to process a complex stimulus, and you will need to begin removing frequencies from your output stimulus to reduce the complexity of the stimulation and enhance your chances of obtaining a response. Some patients may demonstrate difficulty processing a multi-frequency, multi-ear testing paradigm, even at super thresholds. Removing frequencies of stimulation as you decrease in intensities will result in higher thresholds at those frequencies on the audiogram. Fill in the audiogram by returning to the frequencies that were previously taken out, or test them as single ear, single frequencies as you go. It is very common to take a single ear, single frequency approach at threshold levels. As a clinician, you can evaluate your data analysis screen and stop your acquisitions manually. One of the field strategies clinicians take is waiting for a minimum of 80 sweeps to be registered and averaged before making any decisions to stop the acquisition manually. Clinicians look for a repetition of blocks of sweeps in determining their stopping criteria. Most users typically lock in responses anywhere between 120 sweeps and 240 sweeps. You should consider stopping when responses are solid and repeatable. You can also consider stopping your acquisition manually if you are at the end of your test session and you expect the patient to wake up and the patient's state to change, or if testing conditions change that are affecting the signal-to-noise ratios. If there's no response by 240 sweeps and the noise conditions are good, then you will probably not get a response if you continue averaging beyond 240 sweeps. Thus, stopping the test will increase your time efficiency. The maximum number of sweeps, as defined in the stopping rules, are usually only acquired when you are at threshold and the analysis is indicating that you can obtain responses with further averaging. IHS recommends a residual noise measurement of 0.7 microvolts because we have found this value to be the point where averaging more will not increase your signal-to-noise ratio measurement. This is why the auto-stop residual noise is activated and defaulted to this value in the software. This selection can be modified if you find your testing condition calls for a different value. Noise can affect SNRs. Therefore, it is important to instruct patients to sleep and remain still and with their eyes closed throughout the testing period. Keep in mind that eye chirp stimuli are available for use and will result in more robust ASSR responses. Now let's discuss correction factors. The SmartEP-ASSR software tests directly in SPL. This is done to facilitate hearing aid fitting. Yet there is still a need to present the data in HL to compare the ASSR results to the audiometric results. Based on IHS's study comparing behavioral threshold versus ASSR threshold, absolute threshold differences were obtained as shown in this graph. To those differences, we add the SPL to HL conversion factors for long-duration tone bursts to obtain the final correction values for SPL to HL. In SmartEP-ASSR, these values for conversion from SPL to HL are applied when using the General Table option, found at the bottom left of the audiogram window, resulting in a corrected audiogram as shown here. Users of electrophysiological equipment can always calculate their own norms. This can be achieved by recording ASSR thresholds and behavioral thresholds from a group of normal hearing individuals and calculating the difference between the thresholds. Look to obtain the value of the slope and the y-intercept using the values obtained from the threshold search for each stimulus frequency. The regression equation is pure tone thresholds equals the slope times the ASSR threshold plus the y-intercept. The SmartEP-ASSR software allows you to enter in the slope and the y-intercept values from the regression equations to convert your SPL audiograms into HL. We can see here the ASSR regression formula editing window. These values for conversion from SPL to HL are applied when using the General Regression Table option, found at the bottom left of the audiogram window. Audiograms may be generated in one or multiple sessions by simply adding data to any display page and pressing the audiogram button. As discussed earlier, the four main audiometric frequencies are available as eye chirp stimuli. A de Boer cochlear model was used to generate the broadband eye chirp. The narrowband eye chirp stimuli were also generated, taking into account the de Boer model. Each frequency region was approximated by a linear function and expanded in order to allow for better frequency specificity. These types of stimuli have shown in IHS in-house studies to come within approximately 10 dB of behavioral thresholds, improving threshold detection because they can result in more robust amplitude responses, thus increasing signal-to-noise measurements used in response determination. This concludes our ASSR training video. A list of reference articles can be found in the video description. We hope you've enjoyed our SmartEP-ASSR presentation. If you are interested in any of the compatible lines available from IHS, or if you're not currently a Duet user and would like more information on this innovative clinical solution, please contact our sales team at sales@ihsys.com. Thank you for watching. If you have any questions or suggestions, please contact our support team at support@ihsys.com.